Alright, here we are in Chapter 10, and we're throwing on these two sections in Chapter 10 because they're called out in the curriculum outline as things that we need to study. So what you'll notice about 10.1 is I haven't assigned a lot of homework questions from it. It is an extension of 2.4. And so that's why we looked at 2.4 is to prepare us for this section 10.1. So what they're going to do again in 10.1 is they're going to have you look at scatter plots. So as you did that 2.4 homework, you looked at scatter plots. And what it wants you to remember is about the R value. So a positive R value would have this type of shape on a scatter plot. So if this is my scatter plot, this would have a positive R value, where it does look like it's linearly correlated, and the slope of the line goes up. That's a positive R value. If I switch colors to red for negative, which kind of is nice, if you have a negative R value, what that would look like, and I'll go back and still draw this, it would mean that there's linear correlation, potentially, right, if that R is big enough. But a negative R value means that the line's falling. As you try to put the line in there, the line is falling over time. That would have a negative R value in there. And so they're going to ask some questions like that, just like they did in 2.4, but they're going to get at these R values a little bit stronger. The other type of question, and why Chapter 10 is different, is they're going to actually have you calculate the R. They're going to give you pairs of data and ask you to calculate the R value. And so that's going to take a little bit of time as you go through. And so, but what they're going to give you is they're going to give you an X and a Y. And so let me find one that is good for us to look at. So they're going to say X and Y. They may tell you what it's like, in terms of what the data represents, but I saw a lot of X and Y's as I went through the homework. And they're going to have you calculate the R value and decide whether you have significant correlation or not. And so a data set that I'm looking at is pairing cricket chirps and temperature. So one of them is cricket chirps, and I'll let that be the X, and the temperature is the Y. And you're going to have some big numbers: 1188, 93.3. And so I'm going to just do this with a small amount of data. The more data you have, the longer this is going to take you. I'll be cognizant of that as you come to take your test. Now remember, your homework only has 5 problems, right, from this section. And so you'll be able to spend the time that you need. 1286 point, that's an 88. Let me get in there and erase that so you see that better. And 88.6. So 1, 2, 3, 4, 5. We'll throw on another one. They have a little bit more, but I'm running out of space on the sides, and the point would be shown. So this is our data, and they want to know if there's linear correlation between the number of chirps per minute in a cricket and the outside temperature. And so this is the data that they have. They're not asking you to do a scatter plot. They want you to find R. So they want you to calculate R. And just like in 2.4, you're going to compare that R value to a number in the chart. So they're going to calculate R. Now here's the formula for R, and you would want to bring this with you on your exam if I decide that this is going to be on there. I don't know yet, so I will let you know. But if you're reading in the exam review that there's going to be a hand calculation of R, you would want to write down this formula. And the formula looks like this: N times the sum of the X times Y. minus the sum of the x's times the sum of the y's. And that's not its worst part. On the bottom is n times the sum of the x squareds minus the sum of the x's squared, and that's all under a square root, times another square root, which is n times the sum of the y squareds minus the sum of the y's, the whole thing squared. So this is what 10.2 puts on that's a little bit lengthy. Now I have this happening in 2 out of the 5 problems, and the other one R is just given to you. So you're going to have to go through this calculation twice, and I apologize for that, but it's good for you to know where these numbers come from. So as we're looking at this, let's go start to fill in what we can. So R is equal to, well, we know what n is. N is the number of pairs of data. So there's one, let me come along the top here. There's 1, 2, 3, 4, 5, 6 pairs of data. So there's 6 pairs of data. Now I got to get the sum of the x times y. So we will have to create a new row of xy that will be helpful for us. Right? Or you could just have it run in your calculator. So it's up to you whether you create that new row or not. You could literally type in 882 times 69.7. Sorry, I had a typo there. That's the reason for the hesitation. And just write it down. And so you'll be writing down really big numbers, 61475.4, right? And so you leave yourself a lot of room. Or you could just be very careful and take 882 times 69.7 plus 1188 times 93.3 plus 1104 times 84.3. Just checking your calculator each time. So you're not writing down those individual products. You're just keeping it alive in your calculator. Plus 864 times 76.4 plus 1200 times 88.6 times, plus, right? So we want to just be really careful, plus 1032 times 82.6. And you'll hit equals. And so hopefully you have a calculator that you can go back and look at what you put in so you can double check, but it's going to be big. So 522,955.8 is what I got. I would take a moment to double check that I had pluses in the right place and the right numbers plugged in, because you'll not know whether you did it right or wrong until the very end. And so I'm just double checking right now as I'm talking to you. Maybe you're running that calculation again or for the first time. Okay, and it looks like everything is good, and I'm still getting that same answer. So it's 6 times that number minus the sum of the x's. Well, that would be faster, right? 882 plus 1188 plus 1104 plus 864 plus 1200 plus 1032. And I got, for the sum of the x's, 6270. Sum of the y's, 69.7 plus 93.3 plus 84.3 plus 76.4 plus 88.6 plus 82.6. And so it's a very tedious, I was going to say a little tedious, but it's very tedious, 494.9. And that's all over the square root. And let me not make that as big. Come in here with the pixel eraser and come in a little bit tighter. And we know what n is. N is 6. Sum of the x squared, well, we haven't done that yet. So now I got to do 882 squared plus 1188 squared plus 1104 squared plus 864 squared plus 1200 squared plus 1032 squared. So it's a decent homework exercise coming through here. So I got a huge number, 6659604, right? Minus sum of the x's we already have, that's the 6270, and we're going to square that. And then that's times the square root, and again it's 6, and now I got to square these 69.7 squared, plus 93.3 squared, plus 84.3 squared, plus 76.4 squared, plus 88.6 squared, plus 82.6 squared. And so I just make sure that I have all the right numbers, that I have 6 of them, and then hit equals, right? So there's ways to combat that. 41179.15, and then that's minus, and then we know the sum of those is 494.9 squared. And now we got to get this crazy thing into our calculator. And so this is how I would type it in. I would type in 6 times the 522955.8 minus 6270 times 494.9. Now remember, your R value could be positive or negative, so don't put any credence on what that subtraction is. I got a nice positive number out of that, right? I can go back up and look at it in my calculator, make sure I typed it in great. Looks like I did. And so I'm looking at the number 34,711.8. I'm not going to write that down, right? I'll write it down for you, but I wouldn't write it down. It's stored in my calculator perfectly. I'm going to try to keep it. So now I'm going to hit divide by, and then I'm going to hit an open parenthesis, and I'm going to type the square root, and it opens up a parenthesis for my square root. So right now on my calculator I see in this ANS divide, and I put an open parenthesis square root, and it has an open parenthesis. Now I'm going to be typing in 6 times 6659,604 minus 6270 squared. I'm going to close the parenthesis, which is closing the square root, and then I'm going to hit times. So I typed in that 6 times the big number minus the 67, I'll put big, 6270 squared, and then I close the parenthesis, which closed this square root. Now I'm going to hit a times, and I'm going to get the square root again. Whoops, not the right one. Square root again, and now my calculator looks like this. And now I'm going to hit 6 times 41179.15 minus 494.9 to the second power. Close that parenthesis, right? So I did 6 times the 411 and then minus the 494.9 squared. Close that parenthesis, and you don't actually have to close the last one. You can, and then just hit equals, and here's the R value that I got. Super big, 0.9325. So I'll put 0.933. That's my R value. Now what you remember is that there's a chart that was in 2.4. They're going to refer to a chart. Actually, in the homework, they're going to just bring up that same chart. So let me remind you of what that chart looked like. I think I can switch over really quick to the camera. So we're going to go look at that same chart where we were to determine what our critical value is. Now, I think you already know that we have enough evidence for significant linear correlation, but let's make sure. Let me come in here, go to camera, and bring up this chart again. Where is that chart? There it is. Sorry. Now remember, we had 8 pairs of data. So the critical value for R is 0.707. So I in a homework problem that I was working with somebody in 2.4, we had that critical value. So remember, if we're closer to 1 than 0.707, then we say that there's evidence there is sufficient evidence for significant linear correlation. Well, we're at 0.933. So let me come back here and realize that in that chart, 0.707, our critical value is what they call it, was the cutoff to say, well, you got to be closer than 0.707 to call it significantly correlated. So because 0.933 is bigger than 0.707 or closer to 1, there is significant linear correlation between the two values. Now, what were those two values? Those two values were number of cricket chirps per minute and the outside temperature. So it does appear that the outside temperature has a connection to the number of cricket chirps, are definitely correlated to one another and linearly. And so we could use that to predict the number of cricket chirps per minute if we cared at any particular temperature. We would find the line of best fit. Now that line of best fit is what's happening in 10.2. And so as you come to that section, we'll look at those problems as well.